Welcome to section 3.7, the derivative of inverse functions. Basically this whole section really is just like three formulas, and you learn the three formulas and you can do the whole section. So if you wanted, you could watch almost none of these videos. And why am I telling you this? Because I'm trying to convince you why you should watch the videos. I have a dried water droplet on my glasses. That's not the reason why, but basically it's because, at this point, and you may have noticed this already in calculus, but at this point, a lot of the focus is less on computation and more on concepts, okay? More on, do you know why this is the case? Not, can you find the derivative, but what is the derivative? Why can we do this here and not do this here? So these concepts are what I'm going to be focusing on in these videos. So try to follow along and ask me if you have questions about this. And there is a cat that is on my notes, but she has moved. All right, great. So without further ado, let's get started. So we need to remember a couple things about inverse functions. Okay, so there's a couple of big things that we talked about for inverse functions before. And basically, if I compose a function with its inverse, plug one function into another function, those functions should cancel out and just give us back whatever input we started with. And then you can also write that in the other direction as well. If we compose them the other way, plug the other function into the first one function, they should switch as well, or they should cancel as well. Sometimes we wrote it like this as well. I'm saying as well a lot, right? So there's a bunch of different relationships with inverses. The input of one function becomes the output of another function. The x's become the y's, is another thing that is said. Domain becomes the range, range becomes the domain. All the x's, inputs, outputs, x's and y's, they all get flipped for inverse functions. So let's do a little bit of an exploration to see if we can come up with this formula on our own for an inverse function. Actually, I don't want to graph it that way. Let's graph it this way. Let's look at some function. Let's say, call it the red function. It starts at 3, 0. And maybe it looks kind of like this. Well, then what does its inverse function look like? Well, basically, the inverse function, let's make that a blue function, is just what happens when you switch all the inputs and outputs. So instead of 0, 3, it's going to start at 3, 0. And then it looks like it has this point over here. That's 2, 4. That's going to be 4, 2. And then maybe this point, this is like 3, 5. So this is going to be 5, 3, etc. And then it just has the same shape like so. Another way of thinking about inverse functions is they're just what happens when you reflect the original function across this diagonal line, y equals x. Let's call this some function f, and this some function inverse of f inverse. Remember, it's not a negative exponent, even though it looks like a negative exponent, although funny things are going to happen about that. It's just our notation, our weird notation. Let's look at a tangent line, okay? Look at a tangent line at any point we want. Let's look at it, let's look at it up here maybe, I don't know. So up here, this is going to be the same thing as right here. These are correlating points. All right, if this point down here is some input A, in this case, A, it looks to be like 8 or 9. I can't count that high. Well, I could, but I'm not going to. And then it's just whatever the inverse function has a value of that. So the whole idea about functions and their inverses is we can switch between one graph and another graph by just switching inputs and outputs. So this is the point f inverse of A, comma A, right? The input of one is the output of the other. The output of one is the input of the other. So bear with me. I know this is getting a little long, but I want to look at the derivatives of these two functions. What is the derivative, if not the slope of the tangent line? That's exactly what derivative is. If you draw a tangent line to that first one and a tangent line to the second one, what's the relationship between these two lines? What's the relationship between the slope of these two lines? My graph isn't perfect, actually. Let me try to draw a better one. Kind of like that. All right. Well, actually, that looks even worse. All right. It's a hand-drawn graph. It's not perfect. So let's look at the slope. Look at the slope of this tangent line up top. In this picture, it looks like the slope is about 3. But in general, we can say that if we go p units to the right and q units up, like that's how we look at derivatives. That's how we approximate derivatives graphically. Draw little tangent lines and just count the boxes. In this case, it looks like the slope is about 3. So the slope at this point, the slope of f at this input value, right? The input, the x is f inverse at a, is going to be rise over run. And we can do the same thing with the green. Visually, you know, we just count it like this. Visually, it looks like this horizontal change is going to be the same as this vertical change. This vertical change is going to be the same as this horizontal change, right? And again, visually, it looks like it's about 1/3. So what is the slope of this function? The derivative, hold on, how do I want to write this? Actually, the derivative of f inverse at a looks to be about rise over run, p over q. So look at the relationship between these two things, right? So what's the derivative of an inverse function? Well, it's just the reciprocal, right? It's just the reciprocal of the derivative of the other function. So that's all we're going to write. Like let's connect these dots, right? This is going to be our theorem, but the derivative of an inverse function at any point a is just the reciprocal of that. What's the reciprocal of q over p? It's the reciprocal of this. This is going to be 1 over f prime of f inverse of a. And that is exactly the result that we're going to be using in this section. And it looks a little weird, but first off, you don't have to, I want you to try to understand where this comes from, because it looks messier than it is. All it is reciprocal. It's the reciprocal of the derivative. And then we have to make sure that we're evaluating it at the right point, right? We can't still plug in a. We have to plug in the corresponding input. And the corresponding input of f, when f inverse is at a, is at f inverse of a. Okay, so that's our theorem. It's called the inverse function theorem. I'll formally introduce it. I don't do a lot of formal stuff in here, but I'll do it here. Inverse function theorem. Let f be invertible. I haven't used that word a lot before. Invertible just means it has an inverse function. It passes the horizontal line test. It is 1-to-1. These are all things that mean the same. All right. Let it be invertible and differentiable. Then the derivative of the inverse function is just the reciprocal of the derivative of the original function. And then specifically, it's evaluated at the inverse function. Okay. So this may actually look a little bit familiar. You might, hold on, here's our quick little assumption, right? We're assuming that we're not dividing by 0 here. So this should look a little familiar to something, maybe nagging in the back of your head, that we've been talking about the last couple days. So if, I don't want to call this a proof because I'm not going to be very formal, but we know what f of f inverse of x is, right? They cancel each other out. Well, what happens if we take the derivative of both sides? If two functions are the same, then their slopes have to be the same as well, right? Well, the derivative on the right-hand side, we're going to start with that one. That's easier. Derivative on the right-hand side is just 1. Derivative of x is just 1. Derivative of the left-hand side, we need the chain rule. Derivative of the outside function, leave the inside function alone, and multiply by the derivative of the inside function. But we don't know this derivative. We can't evaluate it. We don't know it. Well, what's the relationship between what we have here and this? All we have to do is divide both sides by f prime of f inverse of x. This is just another way of seeing where this formula comes from. So that leaves us with the derivative of f inverse of x equals 1 divided by f prime of f inverse of x. That's exactly the inverse function theorem. It's like super quick. We don't have to do a long, messy proof about this at all. Why is there a red dot up here? All right. And that's where it comes from. All right, let's do one example and then we'll move on to the next video, which is just more examples basically. And some, yeah. We'll get there when we get there. Example 1. Use the inverse function theorem. Nobody abbreviates it this way, but I don't want to write it down. To find g prime for g of x equals x plus 2 over x. Now you might say, Jason, why do we have to use the inverse function theorem? There's 2 reasons. 1, because I said so. It's a terrible reason, of course. This is just for practice. That's the second reason. It's just for practice. We could take the derivative of this as normal using the quotient rule. We could also simplify and take the derivative without the quotient rule. Let me know if you have questions on how to do either of those methods. But let's get some practice using the inverse function theorem and show that it works. Okay? So, to use the inverse function theorem, we need the inverse function. Okay, g is f inverse for what function? G is the inverse function for some function. Let's find what it is. How do you find the inverse function? You switch x's and y's, and you solve for y. I'm going to go through this pretty quickly because this should have been covered in a pre-calculus class. I have extra resources for where this comes from. If this part is not simple to you, which is perfectly fine if you don't remember this, but I don't want to spend a lot of time on it here because I do cover it elsewhere. But eventually you do some many steps and you're going to get the inverse function is 2 divided by x minus 1. This is g inverse, or you can call this is our f of x. We're using that formula from before, and then this is f inverse. These are inverse functions. F and g are inverse functions. If we composed them, if we used function composition, they should cancel exactly to x. If we graphed them, they should be the same function, just reflected across that diagonal line, like we talked about at the beginning of this video. Well, the inverse function theorem says the derivative of f inverse is 1 over f prime of f inverse. The inverse function theorem says that the derivative of f inverse, which is g of x here, is equal to 1 divided by f prime evaluated at f inverse. And again, f inverse is g here. Well, we now remember what we learned about function composition, also a pre-calculus topic, also a topic I have a textbook and videos for if you're curious. Well, this is going to be 1 divided by f prime. Well, it's g of x. You always have to start from the inside. We're plugging in g of x, but what is g of x? It's x plus 2 over x. That's not an x, that's a 2, Jason. So now, how do we evaluate this? How do we simplify this? We now plug this inside in to f. Now, this is where things get a little messy, and you might want to work off to the side here, but make sure you clearly show your work with logical equal signs. But you can still go off to the side and say, okay, let's not worry. We're going to eventually have to take the reciprocal, but it might be a little easier to just look at that denominator by itself. What is f prime of x? Oh, we needed that too. I'm running out of room. What is the derivative of f of x? I'm going to get through it really quickly. You could find it in more steps. It should be -2 over x minus 1 squared. You're going to have to use the power rule and sort of the chain rule. -2 over x minus 1 squared. So if we look at this f prime and plug this in, what do we get? We're going to get -2 over x minus 1 squared. But we're not plugging in x anymore, right? That's what it was here for f prime of x, but we're replacing x with this fraction, x plus 2 over x. So you can see now very quickly how messy this is going to be. And we're going to have to spend a little time, spend a little work simplifying. Okay. And of course, again, we don't even have to be doing this for this problem. This is just practice. My cat is losing his mind. This is just practice. So again, let's hold this thought for a while. We're going to say on next page. And say, okay, eventually we want to be talking about 1 over f prime of x over x plus 2, or x plus 2 over x. But again, let's stay off to the side real quick and simplify this. -2 over x plus 2 over x minus 1 squared. That's not it. Minus 1 squared in parentheses. Oops, got some different color now. That's fine. All right, so that's going to be -2 over... Actually, we don't even need to go off to the side, right? We're just looking at the reciprocal of this. So we can just take the reciprocal right now. Reciprocal is -x plus 2 over x minus 1 squared all over 2. Not too bad. Dividing by 2 is the same as multiplying by 1/2 as well. So we can simplify it a little bit nicer like this as well. We have a binomial that's getting squared, so let's FOIL it out. It's going to be the first thing squared, x plus 2 squared over x squared, minus double their product. It's going to be -2 times x plus 2 over x plus the last thing. And now we utilize a couple of different methods to simplify. Let's combine fractions. -1/2 times x squared plus 4x plus 4 over x squared. We're going to need to multiply in an x and distribute here. Let's distribute first. 2x plus 4 over x. Again, to combine fractions, we're also going to have to multiply by x over x. And the last fraction, we're going to have to turn into x squared over x. Going fast here because we're done with the calculus. We're just doing some algebra right here. And again, it's fine if algebra is unfamiliar. Feel free to ask questions about that. So combining fractions now, we get x squared plus 4x plus 4 minus 2x squared minus 4x. Make sure to distribute that negative plus an x squared over here, all over to x squared. Hopefully, if we combine like terms, something nice will happen. We have an x squared minus 2x squared. That's negative x squared plus x squared. Oh, these all cancel. We have plus 4x minus 4x. Oh, those cancel too. We're just left with negative 1/2 times 4 over x squared. That cancels to 1 over 2. It simplifies to negative 2 over x squared. That is our derivative using the inverse function theorem. So again, the inverse function theorem is not helping us here, but it's showing you how to use it. And if you're curious, why do we learn this if it's not helpful? Oh, we're going to apply it to things that it's helpful for. Trust me. Trust me. Okay, but this is just a little practice. Let's real quick take a moment and compare our answer. This is also a good way to check our answer, right? G of x equals x plus 2 over x. Well, we can also write that as 1 plus 2 over x. Right? If there's addition in the numerator, you can split it up, and x over x is 1. G prime of x, y'all are going to be so angry with me. 2 over x, right? That's just 2 times x to the negative first power. So the derivative of 1 is 0. And then use the power rule, negative 2, x to the negative 2. The derivative is negative 2 over x squared. There we go. It's the same answer, negative 2 over x squared. It took a little less time this way. You could have also used the quotient rule. All right. But it checks out. This is just some extra practice for you guys. All right. And again, this is mostly the end of the video, but I want to just show a couple connections to these topics. Where the heck is my Desmos? Here it is. It was hiding. Let's graph these functions, right? So one of our functions was x plus 2 over x. And what we said the inverse function here, I don't remember what it was. We said the inverse function was 2 divided by x minus 1. So the orange graph is the inverse function of the blue graph. If you reflect one graph over this pink line, it becomes the other graph. That's a visual interpretation of this. Okay? Now let's graph our function and the derivative that we found, negative 2 over x squared. Now is this orange graph the derivative? Look at the slope. The slope is a small negative number here. Okay. The slope function, the output here, is a small negative number, negative 0.025. Slope is negative everywhere. Oh, slope is a big negative number now. Y value of the slope function is a big negative number. Slope is still a big negative number. Slope is still a big negative number. What's the slope of this blue graph here? It's a small negative number. It's still decreasing. And again, the function value of our slope function is still a small negative number, negative 0.056 here. So one of the ways to see the relationship between a function and its derivative function, its slope function, if you will. All right, that ties it all up together. That's pretty much this video. It was a little longer than I thought it was going to be, but the rest of the videos aren't that long. I'm pretty sure. Have a good day and let me know if you have questions.